Hi guys, this is Santosh BTS and my roll number is BT21CME105 and my topic is Raman spectroscopy and introduction to Raman spectroscopy. Basically, Raman spectroscopy is a non-destructive technique and it is used to determine the molecular composition and the structure. And the historical background behind this is it was discovered by Sir C.V. Raman in 1928 and for this he got Nobel Prize in Physics in 1930. And the main significance is it provides molecular fingerprints and complements other spectroscopic methods. Uh, Basic principle of Raman effect. Basically, the Raman effect is based on the inelastic scattering of light. When a beam of monochromatic light passes through a material, most of the light is scattered elastically, which means Rayleigh scattering, and it has the same wavelength as the incident light. However, a small fraction of light is scattered elastically and some small fraction is scattered inelastically, where the wavelength changes due to interaction with material molecules, and which which brings the Stokes shift and anti-Stokes shift into the situation. Basically, the Stokes shift is the scattered light has the longer wavelength, that means lower energy because the molecule absorbs the energy, and anti-Stokes shift. The scattered wavelength has a shorter wavelength, which means high energy, and because the molecules releases energy. The shift in wavelength provides a molecular fingerprint and revealing information about the material's molecular structure, bonding, and environment. Okay, Raman shift refers to the difference in the energy between the incident light and the scattered light in the Raman spectroscopy experiment. It is measured in wave numbers, and it provides the information about the vibrational and rotational and other low frequency modes in a material. And basically, the Raman shift is the difference between the incident and the scattered light energies. And the formula is delta V is equal to 1 by lambda naught 1 by minus 1 by lambda s. Lambda naught is the incident light wavelength, and the lambda s is the lambda scattered, which is the wavelength of the scattered light in centimeters. And um, the significance is the it identifies specific vibrational and rotational modes. Okay, then let's get into the instrumentation overview. Basically, the Raman spectrometer involves the key components that involves in the Raman spectrometer are the laser source. In general, we use VAG lasers and the sample holder to hold the sample, and the filters that removes the Rayleigh scattering. Basically, Raman scattering involves inelastic scattering, so we have to remove the Rayleigh scattering before, and the spectrometer to detect the spectrometer to which involves grating, and the CCD detector which detects the sample. So each component ensures precise measurement of molecular vibrations. The working of Raman spectrometer. Raman spectrometer works by analyzing the inelastic scattering of light to study the molecular vibrations and structures. Light source. Light source is the laser that illuminates the sample, and the scattered light is filtered. Most light scatters elastically, so but a small fraction of light scatters inelastically, and which involves Raman scattering. And we have to collect the scattered light and the filtered to block the Rayleigh scattering. And then we have to do the dispersion. The Raman light is dispersed by a diffraction grating which is in the spectrometer, and after the CCD detector captures and processes the data. And analysis, the Raman shift reveals the sample's molecular and chemical information, and this technique is widely used in material science, chemistry, and biology too. And then the types of Raman spectroscopy. Basically there are so many types of Raman spectroscopy, but we will discuss some of the main types, and they are resonance Raman, and which enhances the signals for specific molecules. Basically, it uses a laser wavelength close to an electronic absorption band of the molecule, and it enhances the Raman signal by several orders of magnitude, and it is useful for studying chromophores, pigments, and biological molecules. And the second one is surface enhanced Raman, and which is also called SERS. It uses metal nanoparticles for sensitivity, and and this is enhanced by molecules adsorbed on rough metal surfaces like gold or silver, and it provides extremely high sensitivity and down to single molecule detection, and it is widely used in chemical sensing and blown sensing, and one of the other type is time resolved Raman, and which studies the transient states of molecules by measuring Raman spectra over short time intervals, and it is useful for investigating chemical and dynamic reactions. Interpretation of Raman spectrum. Here we can see the example of olivine, and in the x-axis we have Raman shifts, and which identifies the peaks in wave numbers which corresponding to specific molecular vibrations, and in y-axis we have intensity or molecular concentration, and higher intensities indicate higher concentrations and or stronger Raman activity, and we have to compare with references match shifts with known spectra to identify the bonds or functional groups, and peaks corresponds to the molecular bonds and vibrations, and basically we have a general range peak regions and 0 to 400 centimeter inverse which have lattice vibrations, and 400 to 1800 centimeter inverse which consists of functional group fingerprints, and 2500 to 4000 centimeter which involves bond stretching. This reveals the molecular structures and compositions in the environment. And Raman spectrometer or the spectroscopy, which is involved in so many industries, and it has also applications in material sciences. It involves in the characterization of crystals and defects, and stress and strain analysis in the materials, detection of phase transitions, and it is also used in pharmaceuticals, identification of drug polymorphs, and mainly it is used in the quality control in formulations, and it has also the ability in monitoring the stability during the storage, and it is also involved in chemistry too, real-time reaction monitoring and molecular bonding and functional group analysis, and it is also involved in research in catalysis and surface interactions. It has also the applications in environmental science and detection of pollutants in air, water, and soil, and it is also involved in the identification of microplastics in marine environments. It is also involved in the analysis of particulate matter in air pollution. So it has a lot of advantages and limitations too. Basically the advantages involves, and it is non-destructive. It is very useful for the non-destructive analysis, and it works for all the solids, liquids, and gases, and it has high specificity. Basically these are the main advantages that involves in Raman spectrometer, and the limitations, and we have also the limitations, which is they are having weak signals, and which requires some enhancement techniques and fluorescence interference, and basically it's an expensive equipment, which is one of the major limitation. And the future trends and developments are, mm, the to overcome the limitations, we are using portable Raman devices for field analysis, and the combinations we can combine this with another techniques like IR or XRD, and we are also using machine learning techniques and AI techniques for rapid and precise spectral interpretation. And the conclusion, and we can conclude this by saying Raman spectroscopy provides detailed molecular insights, and which is widely involved in material sciences and pharmaceuticals and environmental studies, and it is a versatile tool essential for both research and industrial applications. That's it. Thank you.